Thanks,
Hello?
Raymond.
Oh, hi. Yeah, no problem. So let me see. Oh, I think I can make you a host.
Okay.
Okay. I think you're a host. Or yeah. And I guess whoever comes in, whoever needs to be a host, you can make them a host.
Okay, great. Thank you
Yeah.
so much.
Yeah, no problem. Sorry. Yeah, I don't think
Yeah.
I can make it to the seminar today.
Yeah, no, I'm sorry to hear about your son. Yeah.
Yeah, no problem. Yeah, my car got hit by a tree this week, and my daughter is in quarantine this week, so a lot of things happening this week.
Wow. Wow. Sorry. Yeah, there was a tornado warning, right?
Yeah. Were
last night.
you here that night?
Yeah, I got caught in it. I had to wait in the restaurant, but relatively low damage compared to having your car struck by a tree.
Yeah. Yeah. Okay. All right. Enjoy the seminar.
Yeah, thank you.
All
Thank you so much. Yeah.
Okay,
See
no
you.
problem. Bye-bye.
All right. So I think you have to join the Zoom room from your laptop.
Okay.
Hit the recording.
It's my great pleasure to welcome Evgeny Kudzovsky, who is click a button, I guess. Sorry. Got it. So Evgeny got his degree from Dubna, that's the nuclear particle lab near Moscow, and since then he has been pursuing experimental particle physics career in the UK, but working mostly on the experiments located at CERN, doing the kaon physics at high intensity, high precision measurements. He was part of an A48 collaboration. Now that is an A62 collaboration, has achieved numerous important measurements. Of course, most notably K plus to pi plus minibar, and he is looking forward to new opportunities with the kaon physics at CERN, getting even to higher intensities and more interesting rare modes. So welcome.
Okay, thank you very much. Thanks for invitation. Thanks for a very nice introduction. Thanks for coming. So I'm going to be talking about present and future kaon experiments. Well, I've been working on kaon physics for 20 years, and that's why that's the title of the talk. So I'm going to be introducing rare kaon decays first, and then I will cover the current kaon decay program and the future program at CERN, that's the A62 experiment and successors. And I'm also going to cover the kaon program at another lab, which is the J-Park lab in Japan. And finally, I'm going to conclude. So
just maybe one quick comment. We usually have the seminars going on forever, but because this is during the lunch break, for the meeting, we should limit it to 50 minutes.
That's fine. Yeah. Okay, excellent. Thanks for thanks for the note. Okay, so first, why are kaons interested and why are we doing kaon physics? Well, actually, kaon is one of the lightest unstable particles. It was discovered 70 years ago. And it's been essential to establish the foundations of particle physics. For example, CP violation was famously discovered in the kaon system, but also phenomena such as the Jim suppression, quark mixing were established in the kaon system. Kaons are characterized by very high production rates, and therefore there are very large data sets available. We are talking about 10 to 13 kaon decays as a typical current data set. And this leads, along with a very simple final states, to extremely high precision. Well, and actually some of the kaon decays measured and established have branching fractions as low as 10 to minus 11. So when we are talking about rare kaon decays, we're talking about 10 to minus 10 to 10 to minus 11 branching fractions. And the current focus of kaon physics is to look for new physics beyond the standard model with rare processes. And in fact, there is a well-established opinion, a consensus that what we are doing is sensitive to a mass scale of 100 teraelectron volts in terms of the reach to new physics, indirect reach to new physics. Well, there is a number of count decay, so-called golden count decay modes, right? There are a few K long and K plus decay modes. The most interesting ones are those at the bottom of the table. These are the decays of the charge counts and K long into a pion and neutrino-antineutrino pair. Why are they so interesting? Well, they're they're extremely rare. They are flavor changing neutral currents, right? Preceded by penguin and box diagrams. And in fact, if we look at these two particular processes, K plus and K long going to pi nu bar, well, they receive the maximum CKM suppression. That's what brings their branching fractions within the standard model to the level below 10 to minus 10. And importantly, they could be predicted very, very precisely within the standard model. The reason is mainly because they receive no long distance contributions from intermediate photons, and the hadronic matrix element could be extracted directly from well-established count decays. And here I'm listing the two most recent standard model predictions for the branching fractions of this process. You can see that the uncertainties are as low as 5% in each case. So that's a very rare and very precisely known observable in the standard model, the branching fractions of these two processes.
Is it mostly coming from the CKM uncertainty?
So in the past, the main uncertainty was CKM parametric. Now, these new results, actually, it's a new way suggested by Andrei Buras to compute the standard model prediction in a way which is independent of VCD. So only the angle beta actually enters. And the uncertainties are have got two sources. First, the parametric, the beta angle, and secondly, the lattice VCD, well, the intrinsic theory uncertainty. So for the next decade, the expectation is that the 5% precision can reduce to the 3% precision. And anyway, we need to measure this modes to at least 10% precision to make a meaningful comparison between data and experiment. They're thinking about BSM contributions to these models. Well, there have been a lot of studies of BSM contributions, and importantly, the correlations. So here I'm plotting the branching fraction of K long to pi nu bar versus the branching fraction of K plus to pi nu bar in units of 10 to minus 11. And this is the standard model prediction. Well, it's got 5% to 10% uncertainty, depending on your point of view. And one can see, several generic new physics models here, and the expectations of the two branching fractions in this plane within these models. And what's striking here is that certain classes of models predict strong correlations between the branching fraction of K plus and the K long case. For example, the green is the models with minimum flavor violation. The blue are, the Z prime models with left-handed or right-handed couplings. And for this reason, due to these well-established correlations, it's important to measure both branching fraction of K plus and K long to pi nu bar to a 10% precision. This would allow to pinpoint new physics if there is any new physics appearing in these channels. And actually, there are further correlations with other observables like epsilon prime over epsilon, delta and K, and important correlations with B physics, in particular, the hints for electron flavor violation B physics could be correlated within some models to the possible observations in the count sector. Okay, now let me move on to the description of the count program at CERN. Well, CERN has been home to count experiments for many, many decades. And just in the last 25 years, there have been 5 different experiments at CERN. They were all located in the same place. That's the ECN3 hole in the northern area of the SPS accelerator. So the SPS accelerator is marked red on this sketch, and we can see that the experimental hole where the beam is extracted to provide the count beam is more or less in the center of the LHC ring. It's not on the LHC, but it's just in the center of the LHC. Well, out of the 5 experiments which I mentioned, well, perhaps the most famous one is the MA48, which established direct CT violation about 20 years ago. And currently, the most recent experiment is Na62, and I'm going to discuss a few things about Na62. So here is a sketch of the Na62 detector. So how does it work? The SPS protons, 400 GeV protons, are extracted from the accelerator and hit a beryllium target to produce a secondary count beam with a 75 GeV mean momentum and a narrow momentum band. So talking about the rates, the beam rate is 750 megahertz. Well, it's actually dominated by pine. So the count rate is much smaller, and actually the number of counts decaying in the fiducial decay region in the vacuum tank is about 5 megahertz, 5 million per second. So the main detectors are the following. There are the two trackers. There is a silicon pixel beam tracker on the upstream part, and a straw tracker immersed directly into the vacuum volume on the downstream part to measure the products of count decays. So the interesting count decays take place here in a 70 meters long vacuum tank. Then this is complemented by two Cherenkov detectors. There is one on the kiln part to tag the counts, and there is a reach downstream to identify the decay products. And finally, there is a system of colorimeters which form a hermetic system, so no photon from count decays in the fiducial decay region is going to escape the system. This is how it's designed. And indeed, it provides a very good suppression, for example, of pi0 decay to 2 photons at the level of 10 to minus states. Okay, so the largest data set collected so far is a so-called RUN1 data set. We collected this data set between 2016 and 2018. This data set corresponds to about 6 times 10 to 12 useful count decays in the vacuum tank. And in terms of the number of protons on target, it's about 2 units 10 to 18 protons on target. And here I'm actually showing you a photograph of the setup, but you can see it's a very walkable experiment. So if you're ever at CERN, please, well, contact us if you're interested. It's very interesting to actually walk along the same path along which the counts propagate and see every detector. There's plenty of space. It's not like an LHC detector.
I heard that's the longest particle physics detector, right, in the world.
Well, in the broad sense, it's a quarter mile long, right? In the broad sense, starting from the target. Well, it's not where the detectors are, but the whole beam line, the setup of the detector. The detector itself is easily 100 meters long. Yeah.
Just a silly question. The shutdowns, do they coincide with the LHC shutdowns?
Yeah, they do. Yeah, they do. Yeah. So we had a shutdown in 2018 to 2020. Well, actually, we restarted early. The LHC is just restarted, but we have restarted in 2021. We have approved until 2025, the next one shutdown. And we are now collecting a new data set, a larger data set at higher beam intensity. And however, all the results I'm going to be showing are based on RUN1, because this is a fixed data set, fully calibrated and fully established.
Is it going to be an order of magnitude in useful decays?
Almost, I would say, yeah, almost. It's a longer run at a higher intensity, so yeah, it's definitely a lot more than a factor of 2, but maybe not quite an order of magnitude. We'll see how it goes. So in this sketch, well, I'm just showing you the principle of K2 pi nu bar measurements of the Na62. And this plot kind of shows you everything about charge count decay physics. So the 2 key observables are the following. Here we've got the momentum of the outgoing pion, the K2 pi nu bar decay, and here we've got the squared missing mass. And you can see the main features of count decay. So you see the 2 stripes here, which correspond to 2 body decays, right, with fully fixed kinematics, or no degrees of freedom. So you've got the pi plus pi 0 band, you've got the K to mu nu decay band. Then on the top, you've got an enhancement of decay density, and these are the K to 3 pi decays. And then in between, this is where the background for pi nu bar is the lowest. We find our region 1 and region 2. This is where we're looking for K to pi nu bar candidates, right? They're not compatible. It's a single track produced in a count decay, not compatible with coming from one of the major decay modes. So the principle is the following. So in these regions, we suppress the main count decays by 3 orders of magnitude. And for the pi plus pi 0, we suppress pi 0 to gamma gamma by another 8 orders of magnitude. by forbidding any photons in the final state, because we've got a hermetic system of photon torpedoes. While for the muons, we identify the pion in such a way that we reject muon contamination by 8 orders of magnitude. So we get 11 orders of magnitude background suppression. And this is how we get to a signal to background ratio greater than 1. Because we are talking about 10 minus 10 signals, and it's important to get the 11 orders of magnitude here. Well, this is the real data. This is 2018 data set, which is most of run 1 data set. And this is how it looks like before we unblind the signal regions. So you see you've got lots of events on top. These are the 3 pi decays of the charge count. Here you've got the pi plus pi 0. And here you've got the k going to mu nu, right? We've got the 2 signal regions in red, and we've got here.
So pi 0, these are the pions that decay to photons and you don't detect
Yeah,
the photons.
these are the
right?
ones in which we don't decay the photon. This is the residual, exactly. Yeah. So they're already suppressed by a factor of 10 to 8, and this is what remains for 5 times 10 to 12 count decays. You can almost count them, right? But we are starting with 10 to 12 count decays, exactly. Now you can see that here we've got 5 control regions. So what we are doing, we are firstly producing background estimates in the control regions and the signal regions. Then we unblind the control regions. We are happy that there is a good data MC agreement between our estimate and the actual number of events, and then we unblind the signal.
So you never look into the blinded region, or some experiments unblind like a few percent of their data completely, like Babar, and they look into everything, and then they unblind 95% when they.
No, we don't do that. We don't do that. We define control regions instead.
Okay,
So we unblind control regions where the signal is not there, but they're very close to the signal region. So our strategy is slightly different in this sense.
Sorry, just a basic question. So the K2 mu nu case, you don't have pi burst, right? So in that case, the x-axis actually on the side does the mean burst momentum.
So here we are, okay. I think actually it's better to show you this, right? So here we are assigning a wrong mass hypothesis to the muon, and that's why the band becomes bent, right? It's a K to mu nu with the missing mass computed by assigning a wrong mass hypothesis. That's why it's not horizontal. That's why it's got this fun shape. Yeah. Thanks. It's a very good question. Now, I would like to stress that for the conventional backgrounds, which is pi plus pi 0 and K to mu nu, we adopt a data-driven background measurement. What does it mean? Well, we've got some special selections, and we actually measure directly the non-Gaussian tails. Well, so this is the pi plus pi 0 signal. And we measure directly the non-Gaussian tails in the missing mass with a control sample. So we know the exact probability. It's of the order of 10 to minus 3, actually, for the event to end up in the non-Gaussian tails in the signal region. And then we multiply by the residual population of this band, which is determined by the photon veto efficiency. And the product of the two, under certain assumptions, give us the background estimate. So, well, for pi plus pi 0 and KME2 is fully data-driven. We almost don't use any MC simulations at all. Now comes the surprise, and that's quite an unpleasant surprise. Actually, it turned out that most of the background is not the one that we were expecting, right? We found out that the main background in run 1 comes from what we call the upstream count decay. So the count beam, while it's being delivered to the experiment, counts naturally decay to pi plus pi 0. And then, well, there are all sorts of classifications that I'm not going to go into, but this is the most incredible of all, right? So the count can decay here in the spectrometer.
But it is more or less only a small fraction of your chaos decay, right?
Yeah. So the
so
600 meters.
It's uniformly distributed,
almost,
right?
Yeah. So we're talking about an experiment which is 100 meters long, and the mean free path of the count is 75 GeV of 600 meters. So it's a very mild linear slope. Yeah. So they decay all over, more or less uniformly. So some of them would decay in the upstream spectrometer. And then, well, the pion momentum from this decay is lower than the Kelvin momentum. So it's get bent by the dipole magnets in quite an incredible way. And there is one particular case where the pion can actually overshoot our collimator and our veto detector upstream. And the pion re-enters the decay region, and then in time with this count, there is an extra beam particle which provides a nice upstream track. They match, and you get the background. This is totally unexpected. This was totally unexpected, and that's the solution. So the solution is to replace our old collimator with a so-called new rainbow collimator, which helped a lot. It almost doubled the acceptance. But just to make the point, we were working hard to predict our backgrounds, and yet the main background was identified based on the data set, and that's something we didn't even think about properly. And this is a recurring point in this kind of experiment, not just at an A62, but I'm going to be talking about the Koto experiment in Japan, and they hit exactly the same issue. When we are talking about 10 to minus 12, this is what happens, and we are honestly telling you that this is what happens. Now I'm going to show you a busy table, well, which we don't need to understand, but importantly, if you look at the top part of the table, you will see the backgrounds from the conventional decays, pi plus, pi zero, k nu, and the 3 pions. And you see that these backgrounds are well below 1 event in a data set which is expected to contain 10 standard model K2 pi nu environments. And then we've got this upstream background, which is not just the dominant by far, but moreover, in order to decrease it to a certain level, we had to sacrifice a good part of acceptance. So that's really something which is totally a limited factor, a limiting factor to the measurement. Even with the new collimator, it was problematic actually. Finally, we open the box here and we can count events. Here we've got 17 events. That's the 2018 data set. In the full run one data set, we've got 20 events, where we expect 7 background events. And well, this is actually the distribution of the data events and the expected backgrounds in terms of the missing mass. The expected number of standard model events is 10. So this allowed us to establish the first ever evidence and well, measurement of the branching fraction with a certain precision of the K plus to pi nu bar decay, and that's 10 units 10 to minus 11 with an uncertainty of about 40%. Right, that's based on the run one data set. And well, I think that's an interesting plot here. That's a historical perspective over 60 years of both experiments and theory. So we see the experiment has advanced by 6 orders of magnitude in terms of sensitivity over half a century. And in a similar way, theory has been advancing, right? So the G mechanism was established, then some input from B oscillation was put, then isospin correction, and so on and so forth. And the theory uncertainty is shrinking as a function of time, something that we already discussed at the start of the seminar. Well, now the next thought immediately, if you measure K to pi nu bar, why don't you look for K going to pi x where x is invisible? That's a direct reinterpretation of the K to pi nu bar measurement. And indeed, we have carried out this kind of analysis in region 1 and region 2 on both sides of the pi plus pi zero peak. And moreover, we have set up a special analysis to look for signal on top of the pi plus pi zero peak itself. Well, for this, we actually had to re-optimize the selection. So we suppressed the pi plus pi zero peak kinematically. Well, clearly the decay rate of pi zero to nothing, well, pi zero to nu, the standard model decay rate is negligible. So any pi zero to invisible decay rate would be interpreted as a sign of new physics. And these are the results. Well, on the left-hand side, well, it's just a plot to illustrate that we were setting upper limits in the branching fraction versus the mass and the lifetime. When the lifetime becomes too short, the pi nu selection doesn't work because the pi nu selection is requiring that there is nothing in the final state in addition to the pi.
Oh, lifetime to visible stuff.
Yeah, exactly. Lifetime to visible. Yeah, to be precise. Yeah, exactly. And the most interesting plot is the one on the right-hand side. So these are actually the limits on the dark scalar coupling parameter, which were obtained from the analysis. So there are 2 curves obtained from the K going to pi nu, right, on the right-hand side and left-hand side. And in the middle, there is a curve obtained from pi zero to invisible. And well, just going a bit forward, right, there is also a very interesting Koto curve at about 10 to minus 3. Which spans also the pi zero region. It doesn't care actually.
Is that their most recent result? Is that their most recent result, or?
Well, yes and no. So that's the 2015 result. but they've got also 2016 to 2018 data set, which due to an apparent background fluctuation leads to the same sensitivity. So there are
Okay.
two results, and the two curves are, you are not going to distinguish. Well, actually, technically, it is the most recent and not the one called to produce themselves, but that's a technical detail, right? Okay, now, as we started talking about hidden sectors, let me give you a few more examples concerning hidden sectors. So, well, firstly, we have completed the search for production of heavy neutral leptons in count decays with a full round one data set. So we're looking for K going to a charged lepton and another invisible particle of a certain mass. And we are plotting missing mass both for the positron case and for the muon case. So we can see that for the positron case, there is a large background for K to mu decays with muon decay in flight. In the muon case, the background is actually extremely small. Note that this is logarithmic scale. So the standard model signal, K to mu and K to E mu, is centered at zero missing mass. And we are looking for spikes on top of a continuous distribution here. We've got a sample of 4 times 10 to 12 K to E mu decays. That's a huge sample. It's collected with a new trigger line. And we've got a sample of 4 times 10 to 9 muon decays because it's heavily downscale. And these are the results. So we'll put into the context. So we've got the limits on the electron coupling on the left-hand side and muon coupling on the right-hand side as a function of the assumed heavy neutral lepton mass. So you can see that the limits are of the order of 10 to minus 8 for the electron case and 10 to minus 8 also for muon case. So there is a compensation between a smaller number of counts and a smaller background.
So a skeptical person would say that much of it is ruled out by cosmology, right?
Yeah.
Because the lifetimes would be too long, right? That would be, or at least you would need some non-trivial cosmology scenario to be compatible with BBN.
I think this missing angle and this mass is already having too long a lifetime.
Yeah.
No, the 100 MeV is still a long lifetime, right?
Well, speaking about the basic
Which
model,
scale? Which
the lifetime is going to be long.
Yeah, it's essentially the BBN curve follows quite nicely the outline of the lab constraints. And the BBN curve rules out things to lower mixing angles because that's where it gets more long-lived. So your only options are to do non-standard cosmology or to add new physics that makes this thing decay faster, potentially invisibly. And then there is no BBN bound, but there is still an NA62 bound.
What's the seesaw target there? That's just people doing low scale seesaw models.
That's right.
Yeah. Well, from the experiment perspective, this is where the theorists want us to get eventually. And eventually, Kelvin experiments will almost get there, actually, for the electron coupling. And interestingly, there is a new PINE experiment that proved at PSI called Pioneer, and they are improving massively on the pi nu limit. So they will actually touch this bound.
So in that bound, you get the right neutrino masses.
Yeah, exactly.
But because the mass is so low, you need a new fix for the cosmology, right?
Yeah.
but can go back to the previous slide. On the right plot, negative missing mass part, can I say you have an excess? The difference between black curve and the yellow red.
Do you mean here?
The left.
Oh, on the left.
Yeah.
Okay, so sorry, I didn't explain this subtle point well. So these curves are, these far tails are non-Gaussian tails actually. And we are actually using the difference between data and the simulation here to understand how well we simulate the tails. So this is included into the analysis. Right, so this is basically a control region.
Okay.
And then we can use the level of disagreement of the control region to understand how well we simulate things in the signal region. Yeah, but there is a clear disagreement. And well, it's extremely difficult to simulate the very long tails, very long non-Gaussian tails.
Yeah, of course, the signal you're looking for is resonance in the positive mass
Yeah,
part. So you don't concern about this. But if you say there's a disagreement between your simulation and your data, for BSM people, it's access. One can cook up stuff for that.
And
So
actually, that's a very good point. So why we are reaching such a good sensitivity? Because we are looking for signals which are spikes.
yeah.
So if we were to look, for example, for k going to mu x, which we also did, which is not a spike but a continuous distribution, the signals are the limits are a lot weaker because this is essentially a systematics. So this region is good in the following sense: there cannot be any BSM signal. So this is a real systematics, right? This is negative missing mass. And we use this region to understand the systematics. And the problem is the following. We've got pileup in our beam tracker, which is subject to 750 megahertz rate. And it's very difficult to simulate this pileup, and it gives rise to a non-Gaussian tail. So occasionally, rarely, we pick up a wrong beam track, or actually a combination of hits which belong to different tracks, and then you get any mass you like, really. And this is pretty much an unavoidable process. Well, it could be avoided by doing a special minimum bias run, right?
Okay. So the K to mu nu x that would give you that kind of tail. The branch ratio is 10 minus what? 10 minus 5.
So the K to mu x will give you an excess which starts at the x mass here, right? It's
it's to the right.
Bump, right?
But
it's
can
on
I?
the right, yeah.
Okay.
I think it's never negative. That's why.
And we actually put a limit of 10 to minus 6 on K to mu x. Well, actually on this thing, on the standard model decay, mu. But you see, it's 10 to minus 6 versus 10 to minus 10.
So this is a new bound?
That was published in last year, actually.
So, last time I played with this a few years ago, some people were citing results from 1970.
Yeah, that's a new bound. Yeah, that's a new
for that.
Yeah, that's a new uninstitutional bound. So
Okay.
in the HNL paper, we also put this bound, and we actually also put a bound on this decay, depending on the X mass, and it's also in the 10 to minus 6 range. This is totally systematically dominated. I mean, you've got the non-Gaussian tail right here, and moreover, you've got the radiated tail, and then you need to understand both. And if you integrate the background over a broad mass range, you get a 10% accuracy of background estimate. It's very difficult to go beyond the 10%.
And it was very different from the theorist's projection for that channel.
Yeah.
So
I thought it's difficult.
Yeah.
But some people have put papers out saying like we're going to do 10⁻⁹ or something.
Okay, now I think I'm going to skip the part related to lepton number violation,
Right.
because we are limited in time. I will just give you one example. For example, we were looking for a decay K going to pi minus mu plus mu plus. And this is how the standard model looks like with mu plus mu minus. And we've got by far the largest sample in the world. Well, this is actually a partial data set. In total, we've got 25,000 of this. And this is what happens when you invert the size. And we put stringent limits of the order of 10 to minus 11. And this is true for all of the lepton flavor and number violated decay. So far, we've put limits on 6 modes, and more analyses are coming. And the slides are there for documentation, of course. Now I would like to discuss the future program. So what are the next steps? Firstly, we are now collecting data in run 2, which has been approved until 2025. And importantly, we have established the decay and flight technique in run 1. And now what we are doing, we are trying to move the measurement of pi nu bar into a high acceptance and low background regime. So what does it mean? We have modified the setup substantially during the shutdown. We have installed a new beam tracker station. We have rearranged beamline elements. And importantly, we have installed several new hodoscopes. That's one of them. And that's another one, it's a small one, in order to make sure that whenever an upstream decay happens, we don't just veto it passively using a huge collimator, but we also veto it actively by seeing the photons and the pines upstream before they arrive into the decay region. And this is very helpful towards actually bringing the measurement to a 10%, or to a signal to background ratio of 10, roughly. And yeah, we've also improved the trigger and data acquisition. So we're running at higher intensity. We've increased the intensity by 30%. And yeah, well, these are the photos of all the VTOL detectors that we have installed. Well, now it's important to say the following. The SPS fixed target operations foreseen until at least 2038, which actually presents an obvious opportunity for Kenon experiments. And currently we are planning for a long-term integrated Kenon decay program, the SPS, to measure the decays of both K plus and K long with a focus on K to binding bar. And the details could be found in a SNOWMAS paper, which we published very recently in April this year. And here, just for reference, I'm attaching the most recent long-term schedule. For the
K long is much harder because you can't control K long propagation before it
It's much
decays,
harder.
right?
You can't measure the K long because
Right.
for K plus, we actually measure the
Right.
momentum of the K plus and we certify. And moreover, for K plus, we've got a low momentum, a low band beam. Yeah, we've got 75 GeV plus minus 1. Now for a K long, it's going to be 40 plus minus 20. So we don't have any kinematic constraint except for the collimation, right? Except for the fact that the momentum is going to be aligned to the beam axis.
Sorry. So how does this, just a naive, how does this compare with the high Lumi LHC? When does that end?
Well, I think
Is it
it must be
2038? It's
be
the same,
date.
right? It's the same.
2038.
It's the same timeline for the high Lumi. It's
Yeah, yeah,
2038.
they share.
They
the
share it.
countdown.
Yeah.
Mhm.
Because I thought that somehow
Yeah,
high
yeah.
Lumi finished earlier, but you're going to 2038.
Well, things are actually slipping.
Yeah, exactly. That's what happened.
There
I
was a
see.
big change in the schedule due to COVID.
Ah, I see. So
Well,
that's
1
why
or
it
2
slipped.
years, yeah.
Because I thought it was going to be done
Yeah.
by
Yeah, so
2035.
this is actually a March
38.
Previously,
Yeah,
I mean.
yes. No, 38 at least. I don't know if there's.
I
any
see. So
number.
now,
That's why I'm
okay.
saying at least 38.
Yeah.
Oh, okay. I got to
Yeah.
work harder in the gym. Now. I see.
Right, and,
38.
Yeah,
Okay.
so yeah, that's the most recent schedule. And importantly, the extracted beams will be there. This is confirmed that the extracted
Yeah.
beams will be there all the time. And this is what gives us a great opportunity. So the first part of our long-term plan is an in-flight K to binding bar experiment, exploiting the NA62 technique to get a 5% precision on K to binding bar. The challenge is the following. We would like to increase the beam rate by a factor of 5 and maintain the same level of accidental coincidences. So we improve all the timings across all the systems by a factor of 5. So we're looking for a 20 picosecond timing for the key systems.
So returning to this VCB, or rather in your case,
Uh-huh.
VTS, right?
Uh-huh.
Can you sort of phrase it as a measurement of
Yeah, within the standard model, we are measuring VTD exactly.
VTD
directly.
and VTS, right?
Mhm.
Or-
Yeah. If you adopt the standard model approach, yeah. Right. So we are thinking about a new pixel beam tracker and a new straw spectrometer in particular. Well, I'm not going into too much detail because I'd like to cover other things, but all the detectors should be able to operate at 5 times higher rate with a timing precision greater than a factor of 5. Now, the next part of the long-term plan is the K-long to binding bar experiment at CERN, which has been studied extensively, right, with a high-energy K-long beam, and the proposal is known as CLEVER. It's been subject to a lot of studies. So the idea is the following: to get rid of the tracker, because the tracker is a source of photon conversions, and that enhances the background. Essentially, it's a large vacuum tank with a hermetic beta system for the photons and nothing else. And it's very good that the canons are boosted forward and got a 40 GeV mean momentum, which means that we only need to instrument a limited cone in terms of forward geometry. And one of the problems of this experiment is that actually there's going to be a lambda decay background. So it would need a longer decay volume so that the lambdas die out. They die out quicker than K longs. And apparently, well, there's a good chance that one would need to expand the cover. So it's potentially a very big project. It doesn't seem to fit nicely in the 250 meters that
So the neutron you wouldn't detect, and it would appear like the lambda just producing pi zero and nothing, right?
Yeah, it's lambda. Yeah. Well, you've got the pi zero. Yeah, exactly. You can lose. You don't see the neutron. You've got a pi 0 and nothing, which is exactly the signal. That's exactly the signal. And most interestingly, well, last but not least, right, we've got also a hybrid experiment in mind. So one could do something on the boundary of high intensity Na62 and Clever. One could use the K-long beamline as in Clever, and tracking and full PID for secondary particles as in Na62, right? And then the main goal would be K-long to parallel, which are 10 to minus 11. Well, they're also actually golden modes in count physics. Then all sort of standard program, Lepton-Slater violation, ray decays, hidden sectors, and importantly, that's going to allow the characterization of the neutron beam. So we can actually measure the properties of the beam before we remove all the instrumentation. We just steer the beam into a K-long to pi bar experiment. We're just getting started with this idea, but I think it's a very interesting possibility.
So it's not measured yet, right?
Not at all. No. It's a very rare case. It's well, it's as rare as K-long to pi bar, and experimentally it's similar. Well, the problem of this decay actually is the Greenlee background. That's another point. It's potential limited by background. That's a 10 to minus 7, 10 to minus 8 branch fraction.
What's the limit on the branch ratio?
Oh, I don't remember. It must be something of the order of 10 to minus 9, but
it's 10 minus 9 from K.
yeah, but one clear
Must be
one is a
good.
dedicated experiment for this one. It's difficult to measure parasitically. Yeah. Okay. Well, I think I'm going just to spend 5 seconds to mention that there is one more KEON experiment, sir, and that's LHC. They're running a very interesting KEON decay program. Well, firstly, they've got incredible numbers of KEONs produced. Well, the cross sections of the order of 1 bar for KEON production, right? Well, but the short baseline means that LHCb can only do K-short physics. Well, they do K-short and hyper as well, and they are producing very interesting results. For example, the strongest upper limit on the decay rate of K-short to pi mu was published a few years ago by LHCb. And now
Why can't they do like K short to pi plus, pi minus, mu plus, mu minus? That's the one that's not been measured yet.
they can do well. They can do this one, yeah, pi e.
Muse is even easier, right?
Well,
it's almost no phase space, so
yeah,
it's
yeah, that's
suppressed,
what I was
right? But it's still possible.
Well, that's a good question. Probably they can. Well, okay. Typically, if the phase space is extremely small, it means that all the particles travel together. Maybe they'd be difficult to resolve. I'm not an expert actually, but well, there is actually a few nice papers where they outline the physics program, so we could use them as reference. Now I'm going to talk. Well, we don't have much time left. I'm going to talk briefly about the KEON program in Japan. So first, the Koto experiment, which is started to take data. So that's a dedicated K-long to pi bar experiment. Right? So the strategy is not very dissimilar to Clever, except that the beam energy is much smaller. They've got a 2 GeV mean K-long momentum, and they've got only a 2 meters long decay region. So this is a very different scale. Well, and actually the ratio of the beam momenta and decay region lengths is more or less the same for an Na62, Clever, and Koto. And well, the beam is composed mainly of K-long, but with an important neutron and photon component. And it's a hermetic detector. They've got a colorimeter. Well, this is actually a photograph of the detector. They've got a colorimeter, a cesium iodide colorimeter in front, and the hermetic veto system. It's just a barrel made of all sorts of veto detectors. So they have been collecting data. So they've published the best limit so far, K-long to pi bar branch fraction based on the 2015 data set. Then they've collected a larger data set in 1618. And interestingly, I'm going to tell you in a minute what has happened, but the limit on the branch fraction became weaker with this data set. And finally, they've got the largest data set so far, which they've just finished collecting, and they're analyzing a very large data set. So this is what happened with the Koto 16 to 18 results. Well, they've opened the box and found 3 signal candidates. And they've done very careful estimation of background. And they concluded that the background is the expected background is about 1 event. And here it's the same story as in Na62. they've discovered new sources of backgrounds.
When they were unblinding, they were thinking that the background is less than one,
Yeah,
right?
exactly. It was a bit worse than an A62, right? They were started thinking seriously about the background after they've done everything and unblinded. So an A62 understood, we had a problem before unblinding, they understood it after. So eventually, well, that's their publication, right, last year. So the largest background comes from the K of K plus. So we've got the halo of the K long beam, which touches their collimators, produces K plus and K minus by charge exchange. And these go into pi 0 and extra neutrino. And pi 0 is a signature of the signal. Important, clearly, right, the background estimate is consistent with the 3 candidates. So one cannot claim.
But they have to lose the electron on that.
Yeah,
side.
exactly. But they don't have a tracker, right? It's easy.
Okay.
Yeah,
Interesting.
Well, it could be, but also we are talking, imagine we are talking about the 2 GVK long or 2 GVK plus or 1 GVK plus. It's very soft. They go in all directions. It's not like at an A62 go to 75 GVB. It's difficult to lose anything. They are operating very differently. Importantly, they've done a great job on the background estimate. And they've actually, well, I would say that their background estimate is now fully data driven. So they have measured directly the K plus to pi plus pi 0 indicates, despite the fact they didn't have a spectrum, they're purely colorimetric measurements, and they've understood the rate of the K plus halo. So the background estimate is normalized to a measurement, to a dedicated measurement. And similarly, the K long halo rate is also normalized to a dedicated measurement. They were looking for K long to 3 pi 0, so 6 photons, I'll say.
So did they constrain the pencilness of their beam?
Well,
Because
yeah.
by knowing the charge exchange rate, you also know the aperture of the beam.
Yeah, well, somehow, basically, they measured the halo, and which implies that they measured the divergence to a certain extent. Well, they don't need to know the divergence per se. But,
So before that was model driven, now it's data driven.
now it's fully data driven. They've
Okay.
measured well, so actually this is the radius of the center of energy. This is basically, if you like, this is a direct measure of the divergence of the beam. They've got a direct measure of it. And they even have a direct measure of how many of these produce K plus. Yeah. They see K plus in case actually. Well, that's a special run, but still. They see, well, they needed to change the trigger to see it, but otherwise they do. And well, what we can see from here, right? We can see that firstly, this is the single event sensitivity, right? Their single event sensitivity is 20 times the standard model edge fraction, and they already have one background. So what do they need to do? They need to improve their signal to background ratio by a factor of 2. Otherwise, it's not going to work. And that's what they've been doing. So firstly, most importantly, they've installed an upstream charge particle veto. And in 2021, it was actually fully operational, which reduces the count background exactly by this kind of factor, 10 to 20. So they've suppressed this, and they've been doing some other improvements. So actually right now, they're going to restart in 2022, later in 2022, with a higher beam power, and they're entering a low background regime, similar to an A62. They've learned what's happening. Well, you can never say for sure this business, but they've learned what their main background sources were, and they've modified the setup to kill them. So they're entering a low background regime. Well, and this is one of the older plots which hasn't changed. That's their sensitivity projection function of year. And by 2025, they expect to get to the 10 to minus 11 sensitivity, which is one standard model event. So they're really going to start closing in into the standard model sensitivity. And more interestingly, well, at this point, the Kota collaboration is confident that with the experience gained so far, they can put forward a proposal for step 2. And that's to reach 100, well, to be more precise, 60 standard model events in a certain reasonable time scale. But this is going to be a totally different experiment. Kota step 2 is a major upgrade of Kota, similarly to what I've been discussing at CERN. So, well, firstly, they're going to rebuild the beamline to increase their K low momentum to 5 GeV from 2 GeV. They would then need a larger fiducial decay region well, the 2 meters is going to become 15 meters. So they will also need a larger calorimeter. And all of this comes actually with the conclusion that one would need to rebuild the experimental hall. So actually it's a major project, a joint project at the J Park with other experiments. It's an extension of the hall. It's a major thing. Well, and they've just published their sensitivity estimate, and the claim is that they can get signal over background about 1/60 standard model candidates, which is exactly what you need to get a 5 sigma observation table. So very interesting. If you compare Clever and Koto step 2, both are looking for 60 events, probably by chance, with a signal to background ratio of about 1. So well, both experiments have done their sensitivity estimates, arrived at a very similar. Each of them is able to discover at 5 sigma, the standard model process, but they will be running more or less concurrently if things go well. Well, and this leads me very close to my conclusion. Well, just to highlight the opportunity we got in the count sector. So if we measure the tube range fractions to 10% precision, right? We get a very strong, stringent model-independent test for new physics, the 100 TeV scale. And by measuring both decay rates, it is very helpful to get, well, to enhance the possibility of observing deviation from the standard model prediction, because the correlations between the 2 observables are crucial. And this is actually a possible picture by 2025, right? So by 2025, Koto will be, well, reaching and crossing actually the 10 to minus 10 boundary for the branching fraction, while the next 62 will be making a 10% measurement. Well, I'm not saying that, well, I'm just fixing here the central value of this projection to the one that we've got at the moment, right? And this is how things can look potentially with respect to standard model prediction. And then by about 2035, 2040, when all the experiments I've discussed have been done, it's a long-term prediction process, obviously, there is a 5% measurement here and a 20% measurement here, right? And this is really something that could...
And the central value there is fixed by your central value?
So the central value here is fixed by the current A62. And here I've just chosen 2 times the standard model. Well, it's just an illustration. I'm not saying that new physics is going to be discovered, right? I just need to put a line somewhere. And this is where the, well, these are the 2 conditions which define the line, the width of the band and the position.
This is like an optimistic scenario.
Yes.
Oh, yeah. Well, it's optimistic in the sense where the central values are.
Yeah.
But probably, well, I would say it's optimistic even in terms of the width of the band, but also it's realistic to some extent, right? This is what we're trying to do. And well, also one last thing to add here, there will be a broad physics program all along. It's not just measuring 2 numbers in 15 years. It's measuring, it's looking for hidden sectors, measuring all sorts of rare decays, lepton flavor universality test, lepton number violation, lepton flavor violation at 10 to minus 12. So it's a very broad physics program.
But mostly by an A62, right? Koto didn't, that doesn't sound like they have.
Well, Koto are doing a few hidden sector searches, but much less. Well, they don't have a tracker for that.
That's what I was.
Yeah. While an A62, I would say, is a general purpose experiment, and the next stage is going to be still general purpose, exactly the same principles. Now, the hybrid K-log experiment with the spectrometer will be general purpose, and only the dedicated K-log to Pioneer bar has no chance to be a general purpose. Because as soon as you put a tracker, you can forget about your main goal. You become a general purpose, except you're not going to measure K-log to Pioneer bar. That's the current consensus with the field. Okay. So just to conclude, well, I already mentioned that the precision measurements of both K plus and K long are essential to get most of this field. And it's actually a very, K-physics is a very active field experimentally. We've got 3 operating count experiments, of which 2 are dedicated just to counts. So by 2025, to conclude, an A62 is getting to 10% precision. Koto is aiming at standard model sensitivity. And the next generation, well, there are 2 very ambitious programs. They will being developed at CERN and in Japan. And well, the action has to be taken right now. I think it's a great opportunity for new groups to join any of the SHU programs. And I'm going to give a similar talk, but less focused on chaos next week at the SnowMass workshop in Cincinnati. And I would like to bring forward the same message. They are medium-term initiatives, not very expensive. They provide great insight, great training for students potentially. And I think now is the right time to join. Please get in touch with us in case you're interested to join.
Very good.
Okay. Right, so thanks very much. I hope, well, I was aiming at
Yes,
half
yeah, that's
past.
precisely on time.
So just quickly, this 100 TeV mass scale is obviously an effective scale, but if you were to put a model there like Susie, what's the scale of the super partners, do you know?
It would depend, right, on the flavor mixing and so on. If you're the
But
problem,
realistically-
like if you have a square mixing, right? You could generate this out of the box diagram, but usually you would also generate K0 bar mixing term, and that would be even more sensitive than the decay, right?
I see.
So the typical lore is that the mixing and the CP violation in the chaos sector are the most sensitive observables, right? But it doesn't mean that it's always like that, right?
But the scale of the super partners then is much lower than 100 TeV.
Ooh, no, if you just take super, this is what's called in good old days was called flavor Susie problem, right?
Yeah.
So if you take a super partner at the TV and you make them violate flavor, you will get like way off, much larger splitting in the chaos sector. And
But let's say you did gauge mediation, right? Which
oh,
is,
and it's fine, yeah.
Because
Then you avoid flavor breaking, right?
and then the limits on the super partner masses would be the equivalent of like a TeV then with this.
That's correct. Yeah. It would. If you have a flavor blind Susie breaking, I don't think you would generate
sensitive.
any of that.
Yeah, you'd be
Yeah.
sensitive. So you have to be lucky that maybe.
So if you're away from more generally from minimal flavor violation, then you're going to get large effects. Yeah. One question I had regarding the CAN experiments, I remember long, maybe 5-10 years ago, I was like following, and then there were some stopped CAN experiments at J Park. Do you know if any of them go?
Yeah, I think you're referring to track.
Track, yes.
Yeah. So yeah, that was a stopped count experiment
Right,
with more or less a 4π geometry,
right.
aiming for KHU over KMHU. That's a test of lepton flavor universality.
Yeah, measuring the
case.
muon momentum and the electron
Yeah,
momentum.
exactly.
Right?
Yeah. Well, I think somehow they haven't been successful in accumulating a large enough data set.
Okay.
So currently the best test of lepton flavor universality in this particular channel is the one that was done at CERN in 2007 by the predecessor of NA60 That's got a 4 per mil precision.
Right.
While I think they even statistically didn't get to 1%. And, I understand they gave up. So, well, they did actually publish a paper of K going to E nu gamma on the rate of the structure-dependent emission in this channel. But yeah, in the end, they are statistically not competitive. I think they gave up actually on this measurement. And the data taken was a long time ago, probably at least 5 years ago, right?
Yeah.
Maybe 10 years ago.
Is there any chance of stopped KN for neutrino physics? What is it? K pipe?
K-pipe, yeah. I've heard talk about it in the context of the upgrade to the Fermilab beam, but
Well, I think a general understanding in the field, at least from the experimental point of view, the decay and flight experiments work better because it's easier to control, to provide the hermetic veto coverage and to control.
If you want the neutrino physics out of it, right?
That's a different story.
Yeah, K-pipe was like stopping chaos and seeing like, again, sterile neutrino, like they still seeing the neutrino interaction as a function of distance, right? But,
Well, in this connection, maybe I would like to make one more remark that I think there is a chance at this experiment, at an A62 actually, to observe for the first time tagged neutrinos.
yeah, I heard this.
I was
from-
going to ask this question,
Yeah,
but
I think we're very close. We did do a proper computation. Well, we haven't presented. It's going to be presented soon.
So it's in the colorimeter, you will
It's a
have.
colorimeter, yeah, exactly. So you've got the production of the neutrino is extremely well measured, right?
but you don't measure the energy of the neutrino very well, or do you?
No, you measure it very well to per few per mil precision. You know the Kelvin energy to a
Well,
few
one
per mil
neutrino-
precision and muon energy to a few per mil precision. So you've got the neutrino momentum.
No, but I mean in the detection, when you see the neutrino
No, in the
interact.
detection, I think what the current goal is the following, right? Just to see the inverse beta decay in the colorimeter and correlate it in terms of direction and time to the production. So just to certify that, look, that's the neutrino. We've seen it's produced and we've seen it interact. Right. Well, we probably are not going further than this, but as a proof of concept.
Yeah, I thought about this, but I didn't know what to do with it.
Maybe I could see the disappearance of neutrino.
But there is no oscillation
Yeah, I
at
don't
these.
think there's
energies.
much to be done, but it's a proof of concept in the following.
Right,
sense,
I think it's
So in
amazing.
order to do it at all, you need a very good beam tracker because you need a lot of counts to come in order to generate enough neutrinos that some of them will actually interact. You need 10 to 12 neutrinos,
Mhm.
absolute minimum 10 to 12 in our conditions.
Why can't you?
Maxime,
Yeah, we gotta stop.
No, no, you guys.
Yeah.
I gotta.
Well, thanks
Probably
very
head
much.
off, but- oh,
We're
yeah.
the rest-
Thank you very
the
much.
rest-
Very nice.
the rest, Ask private.
Yes,
So if
thanks.
they came.
I'll stop recording. when-
Alright.
Okay.